Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of palindrome check. This is a pretty straightforward question. It basically gives you a string of characters and asks you to write a function that determines whether or not that string is a palindrome. A palindrome is a string that's written the same forward as backward. So in front of me, I've got an example, A, B, C, D, C, B, A. And this is indeed a palindrome because it's written the same forward as it is backward. Now, this question is pretty simple, but it's also really cool because you can solve it in a lot of different ways. And each of these ways kind of teaches you something about algorithmic thinking and about algorithm optimizations. So in this video, we're going to be covering roughly 4 different ways of solving this exact question. We'll start with a pretty straightforward way, and you might have even come up with it yourself right now, and that's to basically create a new string that's going to be the reversed version of our input string. So we're going to create the string backwards, build it up backwards, and then compare that new string to the input string and just see if they're equal to each other. And that will basically tell us whether or not our input string is a palindrome. So to do so, we might do something like create a variable called new, initialize it to the input string, and then start iterating through our string, right, with an index I that we initialize as the last index in the string, and we go all the way to index 0, where we have the first letter A. And at every point in this sort of iteration, this sort of for loop, we would do something along the lines of new plus or equal to, string. Let's say our input string is called string of I. And here I'm really writing a lot of pseudocode. We'll go into the actual code walkthrough a bit later on in the video. But so this is what we would do, right? And at the very end, we might say something along the lines of, return new equals string. And once again, this is string. This is our input string. So this would be a perfectly valid solution. And, for this particular example, this return statement here would actually return true because, new would be A, B, C, D, C, B, A, which is exactly the same as A, B, C, D, C, B, A. This is a palindrome. Now, what's the space-time complexity analysis of this particular implementation of the algorithm or solution to this problem? Well, the space complexity should be pretty straightforward. It's going to be O of n, where n is the length of our input string. And why is it going to be O of n? I'll write it here. It's going to be O of n because we're basically creating a new string of the same length as our input string. So O of n, pretty straightforward. But then the time complexity, you might be inclined to say that the time complexity is also O of n, right? We're just iterating once through the string, the input string. But it turns out, if you're an astute algo expert, you'll notice that the time complexity is not quite O of n. It's actually O of n squared, because when we build up this new string and we do this new plus equals string I, we're recreating a new string, right? The way string concatenation works, at least in Python and a lot of other languages, if you do new, where new is a string plus equal to string I, you're actually creating a new string and iterating through all the values in new, or through all the characters in new, and adding them to that new string, and adding string of I. And so, because of that, this actually turns into an O of n squared algorithm. Okay? So, how can we improve upon this? How can we make this better? Well, you might say, instead of creating a new string, let's just store everything in a list, in an array, and then at the end we merge or rather join the list into one string and then do the comparison. And that would be a perfectly valid approach. So here we can say, okay, instead of initializing new to an empty string, we initialize it to an empty array, an empty list. And when we do our iteration, backwards through the string, instead of saying new plus or equal to string of I, we'll say new dot append or dot push or whatever the method is in your language of choice, string of I, right? And so we keep pushing these letters into the array. So we push A into the array, B into the array, C into the array, D into the array, etc. And then at the very end, instead of returning new equals string, we do something along the lines of, and here I'll just write pseudocode, but new dot join, right? Again, this is pseudocode, but that's what we do. We kind of join the array into one string, which would be probably an O of n operation, and we compare it to string. But so that's a lot better than our previous solution, because appending to a list is a constant time operation, whereas doing that string concatenation thing, which creates new strings, wasn't a constant time operation, which is why we had this O of n squared. So here now with this new solution, we actually turned this O of n squared time into O of n time. So we've got O of n space, O of n time. All right, awesome. Can we do better? Or maybe let's not ask can we do better, but can we do this in a different way? Is there a different way to solve this problem? How about we explore recursion? Because so far we've solved this iteratively in two different ways. Both times we were just doing a loop, backwards through the array. But so what if we used recursion? Okay, how would we use recursion to solve this problem? Well, notice that when we are looking at this string, A, B, C, D, C, B, A, and we want to know if it's a palindrome, we're basically saying, is the first letter equal to the last letter? And is the string in the middle, the resulting string, a palindrome as well? Right? So to determine whether A, B, C, D, C, B, A is a palindrome, we're saying, is the first letter A equal to the last letter A? And is the string in the middle, in between the first and last letter, a palindrome? So by applying this logic and by approaching this problem this way, we can use recursion, right? We can say something along the lines of, let's say we have an is palindrome function, and here I'm going to write pseudocode for the most part, but we can say, we can have some kind of base case. So whenever we arrive at the middle of the string, we have some kind of base case that just, returns true. And otherwise, we can say, well, if the first letter, let me give myself a bit more space here. We can say, if the first letter, I'll just write first, is equal to the last letter and is palindrome, we kind of call our is palindrome function on middle, right? I'll just call this mid, the string in the middle. So if these two things are truthy, return true, right? Or we could even not have this entire if statement. We could just say return this, right? Return the fact that first is equal to last and is palindrome on mid. Call is palindrome on mid. So that would be a way to solve this function recursively. And again, we'll go into the exact implementation of that in the code walkthrough in a little bit. But this is the main logic behind the recursive solution to this problem. Now, let's analyze this recursive solution in terms of space-time complexity. How does it fare against the others? Well, in terms of time, it seems like it's also going to be O of n, right? We're first checking we're first checking the first and last letter, A and A, and then we're calling is palindrome on the middle string, which is going to check the second letter and the second to last letter, B and B, and call is palindrome on CDC, which is then going to check that C is equal to C, and then call is palindrome on D, and then we're going to hit a base case and we'll be done. So we're not iterating through the entire string, we're just doing kind of half the work, right? Because at each point we're comparing the first and last letter of a string, but it still converges to O of n, right? We're doing O of n divided by 2 time, or O of n divided by 2 kind of operations, which converges to O of n. So here, for this recursive solution, we still have our time complexity of O of n. What about space complexity? You might be saying, hey, we're not building a new string, we're not doing any of that, we're just like returning the values of comparisons, right, and is palindrome, so we're not storing anything. So the space complexity is just going to be O of 1. And the truth is that's not really the case, because you have to remember that when we're dealing with recursion, there's always additional memory usage, right? Because of the call stack. When you call a function, it goes on the call stack typically. And you have to kind of store the state of that function there while it's being called. And so if that function calls another function, then, which could be itself, in this case it is itself, it is palindrome, then you're adding a frame to the call stack. So here you can literally imagine if we have like a bucket that represents the call stack, right? We'll start by calling is palindrome on our given string, A, B, C, D, C, B, A. And so here, we're going to say, okay, return first equals last, and is palindrome of mid. And mid is B, C, D, C, B. So now we add to the call stack, we add is palindrome of B, C, D, C, B. And we haven't finished, we can't like ignore this A, B, C, D, C, B, A. We can't get rid of it because we're still waiting on the result of is palindrome of B, C, D, C, B to get the result for this. So this has to stay on the call stack. And so, then we get this, then we call is palindrome of C, D, C, and then of D. Okay? And so you can see that we have all these things in the call stack, and all this is like memory being used, and so our space complexity converges to, becomes like O of n divided by 2, which converges to O of n. So our space complexity is the same. It's O of n. Even though we're not storing an additional string, but it's the memory usage because of the recursion and in the call stack that's bringing us to space complexity of O of n. Now, you might have heard about something called tail recursion, or tail calls, which it's a notion in programming that if you call a function at the very end of a function, then you sometimes the call stack, or the location on the call stack where your current function is stored, can just be replaced with that final function that you're calling in the function. And so in recursion, oftentimes it's said that if your recursive call is the absolute final thing in your function, then you actually don't need to store the state of your original function, and you can just replace that frame on the call stack with the new recursive call. So if we can somehow put is palindrome here as the very last, on the very last line of our function, then we might not actually need to store all these different recursive calls in the call stack at the same time. We can just kind of keep replacing them, and we can turn the space complexity into O of 1 space, actually. Now, the thing about tail recursion is that it's a bit tricky because, some people will even claim that a non-tail recursive function can be turned into a tail recursive function by the compiler. In other words, if you're doing the recursive is palindrome function and your is palindrome is not the absolute last line in your function, it's like it's in this return statement that I've written, for instance. If you have a good compiler, the compiler might turn this into a tail recursive call. It might interpret this in a certain way and bring this is palindrome down to the last line and turn that into a tail recursive call, which would optimize your algorithm in your code. Now, it's hard to say whether or not that is the case all the time, and so what I would advise you to do is if you're in an interview and you're dealing with recursion, always acknowledge that recursion might involve additional memory or space usage because of the call stack. And then discuss with your interviewer how something like tail recursion might affect that. You can get into those details in a conversation with your interviewer. But don't jump into a recursive solution thinking that you're just going to have absolutely no space usage, because also a lot of times you're going to be implementing recursive functions, and the recursive calls are going to be in the middle of the function. And so from that point of view, it's definitely not tail recursive, and it definitely adds space usage. So just keep that in mind. Now this brings us to the final way to solve this problem, which is probably the best way, and that's iteratively, but differently than we did at the beginning. The idea is we've determined that we've come up with algorithms that take O of n time, and it's obvious that we're not going to be able to do better than that, right? Because we have to iterate through this string somehow to determine that it's a palindrome. But maybe, as we saw in this recursive solution, we don't have to store some kind of new string, right? And maybe we don't need to use recursion that might end up, using additional space. So how do we do this? Well, we can do this with pointers. We can start with a pointer above our first letter, above A, and with a pointer above our last letter, A. Compare the two, and if they're equal to each other, keep moving. If they're not equal to each other, then just return false. We don't have a palindrome. So when I say keep moving, well, here A and A are equal to each other. So we move the pointers to the second letter and to the second to last letter. Are they equal to each other? Yes, they are. So now we move them to C and C. Is C equal to C? Yes. So now we move them to D and D, and now the pointers overlap, and we're done, right? And this is a palindrome. So that's the fourth way of solving this problem. And this way is going to use just O of one space, because we're literally not storing anything apart from our pointers. We are not storing any additional string, and we're not doing any recursive calls that might add space usage. So this is the most optimal way of solving this problem. And now let's dive into the code walkthrough of all these solutions. All right, we've got our isPalindrome function defined. It takes in a string, and we're going to start with our first solution, the one that we covered at the beginning that involved building the reversed string. So we're going to initialize this reverse string to the empty string, and then we're going to say for I in range, or rather in reversed range len of string, meaning we're starting at the very last index in the string, and then going all the way to index 0. And so at each of these iterations, we're going to say reversed string is going to be plus equal to the letter or the character at index I in the string. And once we've finished building this reversed string, we can just return string equals to reversed string, right? We're testing whether or not our input string is equal to our reversed string that we just built. And that's our first solution. Pretty simple, only 5 lines. And that's going to run in O of n squared time and O of n space. And we kind of explained why that was during the conceptual overview, because we're doing these string concatenations, which create new strings, which take time, right? These are all O of n operations. And we're doing a total of n of them because we're iterating through the entire input string. So n represents the length of the input string. Now we can get into the second solution. The second solution is pretty similar and pretty simple. Let's just comment this first one out. This one is just going to involve having an array. So we can call this reversed characters, reversed cars. And in this array, we're just gonna append string of I, right? So we're doing the same sort of for loop, except we're just appending our current letter or current character to our array of characters rather than creating a new string. And so at the end, we're going to say return string equals, and here we can do, the empty string dot join reversed chars. We can join our characters into a string and compare that string to our input string. So this is going to be O of n time and O of n space. Awesome. Now we get into the recursive solution. So the recursive solution is a bit different. We can't just copy paste like we did for the second solution. For the recursive solution, we're going to take in a string, and then we can also take in an index. The way I'm going to solve this is I'm going to take in index I, meaning at what is the first index that we're looking at in this recursive call. And we can actually initialize this index to 0. In other words, if we call the function without I, we just default it to 0. Because when we first call the function, is palindrome of string, we don't expect to be calling it with an index. And so now we're going to say j is going to be equal to the length of the string minus 1 minus I, right? If I is equal to 0, then j is equal to len of string minus 1, the last index in the string, minus 0. We're comparing the letter at index 0 to the letter at the final index j. If I is equal to 1, then here, we have minus 1. And that's how we can kind of dynamically calculate j at each recursive call. And then if we want to be, we want to show off our recursive skills, we can just do a one-liner here and say return true if I is greater than or equal to j. In other words, if we get to the middle of the string, if we're either at one character left or we're past that, our index I is behind our index j, then we're done, right? We've hit our base case, we return true. And here we're kind of, we're using a ternary operator, right? Otherwise, if I is not greater than or equal to j, we return string of I equals string of j. The first letter is equal to the last letter. And is palindrome of string I plus 1, right? We give the same string, but we say the starting index now is going to be I plus 1. So in this case, it's no longer going to be I equals 0. It's going to be I equals 1, right? We're comparing the string that starts at index 1. And j is going to be calculated appropriately in the recursive call. Now, as we covered in the conceptual overview, this is going to be O of n time, but it's also going to be O of n space because of the call stack, all the function calls that we have to kind of keep storing in the call stack. By the way, let me comment this out. Now, I will note, here, if you wanted to turn this into tail recursion, you might do something along the lines of this. You'd have the same kind of logic behind the function, but then you just, instead of doing this in a one-liner, you'd say, if I greater than or equal to j, return true. If string of I is not equal to string of j, then return false. And then once you're past all these if statements, then you return is palindrome string of I plus 1. Now, the thing is, again, a lot of this tail recursion stuff depends on the compiler. There are some compilers that won't even optimize something because of the tail recursion. In other words, tail recursion might not end up saving you anything. This is just something that's worth keeping in mind and mentioning in an interview, but you don't want to exclusively rely on that, and you never want to make the mistake of thinking that a recursive algorithm doesn't use up any space, because in a lot of cases, or in most cases, it will use up additional space because of the call stack. But this is how you would turn this function into a tail recursive function. Now let's dive into the final solution, the iterative solution that had the base space-time complexity analysis, or the best space-time complexity analysis. So is palindrome is just going to take in a string, and we're going to say left IDX is equal to 0, right IDX is equal to len of string minus 1. So we're saying initialize the left pointer to the first index, initialize the right pointer to the last index, and then say while left IDX is less than right IDX, while our left pointer comes before the right pointer, if, and here we compare whether the two letters at both pointers are equal to each other, if string of left IDX is not equal to string of right IDX, then we return false, right? Otherwise, if both letters are equal to each other, then you increment the left pointer, right? Left IDX plus equal to 1. And you decrement the right pointer, right IDX minus equal to 1. And then once you get to a point where both pointers overlap each other, in other words, they're pointing to the same letter, or they're past each other in the case of an even length string, then you're out of the while loop and you're done. You've never hit this if statement. You've never hit the condition where the letter of the left pointer is not equal to the letter of the right pointer, and so you're officially dealing with a palindrome, and so you can just return true outside of the while loop here. And so this solution is going to run in O of n time, but it's going to run in O of 1 space, because the only two things that you're keeping track of are your left and right pointers, and that's just constant space, right? Nothing depends on the size of your input string in this solution, at least not in terms of space complexity. So that's our palindrome. That's our palindrome function, is palindrome. As I mentioned at the beginning of this video, this is a simple question. You should definitely get comfortable with this, because a lot of questions will actually involve palindromes, and they might start out by having you implement this, and then you'll move on to a much more difficult question that involves, palindromes, and you'll be using this function for the more important problem. But what's awesome about this function is that it teaches you a lot, right? It teaches you how to use pointers to optimize in order to not have to store stuff, how to maybe use an array instead of building a bunch of new strings, or maybe how to use recursion if maybe your interviewer asks you, oh, I want you to solve this recursively. Talking about tail recursion, right? Try to familiarize yourself with all these things. Perhaps even look up tail recursion and do a bit more research on that by yourself, and just be familiar with this question of is palindrome, be able to implement it very fast, and understand it. I hope this video was helpful. I hope it was informative. I will see you in the next one.